Good afternoon, and thank you for joining me today. As I've been introduced by Marco, I'll just reiterate my name. My name is Tracey Najafpour Navaei, and I'll be presenting my upcoming paper entitled Carbon Footprinting of Linear Transport Infrastructure, a Standardized and Consistent Data Collection Method. My sponsors and supervisors are as detailed on this slide. Some quick background on my research before delving in. My research is concerned with carbon footprinting of small network rail geotechnical solutions, with my focus being on earthwork interventions of around 100 linear meters. From the carbon footprints, which are split by life cycle stage, the carbon hotspots in these types of interventions can be found and suitable decarbonisation strategies suggested, all with the goal of assisting Network Rail to reach net zero by 2050. In this presentation, I shall present the novel data capture form developed as part of this research as a proposed instrument for use with any carbon footprint tool and for both rail and other linear infrastructure such as highways, to provide a standardized and consistent data collection method prior to the carbon footprint stage being undertaken. From this slide, you can see the outline of what I'll be presenting today. I'll provide you with an introduction, some background, the method used, some results, discussion, and wrap up with some conclusions. Beginning with the introduction. To indicate the scale of the carbon challenge facing the UK, here is the total UK carbon emissions, transport emissions, and rail emissions, with reducing quantities as indicated, taken from DEFRA 2019 sources. As you can see, the total UK carbon is 454 million tonnes carbon dioxide equivalent, with transport accounting for around a quarter of that, and rail accounting for around 0.4% of the UK total. In addition, the sixth IPCC report highlights the ongoing climate emergency and the near linear relationship between temperature rise and cumulative CO2 emissions, with UN Secretary General Antonio Guterres saying that we are no longer in the era of global warming, we are now in the era of global boiling. There is also an obligation in UK law to reach net zero emissions by 2050, with measurement of carbon being the first and most critical step in carbon reduction. Historically, the focus of transport emissions has been at point of use, with operational carbon being explored at length. However, whole life cycle analysis has grown in recent times, and other life cycle stages are now being included in footprints. PAS 2080-2016, the publicly available specification for carbon management in infrastructure, provides guidance to implement carbon management. This slide indicates the four main stages in the infrastructure assessment life cycle: A, B, C, and D. Carbon footprints will aid in hotspot identification by the relevant life cycle stage, which means that decarbonisation efforts can be targeted at the hotspots in the relevant stage. Baselines, however, need to be set by businesses. As Marco said in the introduction here, Network Rail have set a 46% reduction on their Scope 1 and 2 targets and a smaller reduction on their Scope 3s, with an additional target of 75% of their value chain, that's their Scope 3 emissions, to have their own science-based targets, which are the incremental steps needed to get to net zero by 2050. And using these, a trajectory using these science-based targets can be plotted, as Network Rail have done, using the Science-Based Targets Initiative. For this research project, the baselines are being set in the before use stage of A1 to A5. The A0 life cycle stage will be included in the comprehensive scenario, which I'll come to shortly. I'll outline the different stages of the PAS 2080 infrastructure assessment lifecycle as illustrated on the slide here. The before use stage on the left encompasses A0 to A5, including, as you can see here, raw material supply, transport and manufacture A1, A2 and A3. These are usually lumped together in one embodied carbon footprint for materials, such as those found in the Bath Ice database, where you would find an A1 to A3 carbon footprint for items such as steel, cement, etc. And these encompass the life cycle stages as indicated on the slide. The A4 and A5 are the transportation stages of construction, i.e. the transport of the materials to site and the plant and equipment. And in A5, the construction and installation processes, such as the heavy machinery and hand tools used on site. The use stages in the middle here encompasses B1 to B9, which includes use, maintenance, repair, replacement, refurbishment, and the operational uses. The end of life stages encompass C1 to C4, including deconstruction, which can be thought of as the inverse of construction, transport of the materials away from site, waste processing, and the disposal. Beyond the life cycle is bounded in the D stages, and this would include the negative emissions technologies such as and things such as sequestration, reuse, recycling, and modal shift. These would all be outside of the life cycle of the infrastructure. Moving on to the method section, there are 5 broad steps to performing a carbon footprint as outlined by Williams et al. And as detailed here in the numbered bullet points. 1. All emission sources identified. 2. Determination of which sources are relevant to be included in the footprint. 3. Appropriate method for translating the measurable activities to kilograms of carbon dioxide equivalent. 4. Data gathered and method applied to calculate the kilograms of CO2e. And 5. Method thoroughly documented. The flow diagram in the middle of the slide here demonstrates the alignment of the GHG protocol steps: identify sources, select calculation, collect data and choose emission factors, and apply calculation tools with Williams et al.'s 5 steps. And on the far right of the slide, the flowchart illustrates the alignment of the GHG steps in the middle with the method used. The novel carbon calculation data form being completed, an Excel sheet created to do any transposition of weights into the correct units, and then finally input into the carbon footprint tool, which for this example is the Rail Safety Standards Board Rail Carbon tool. The flow diagram on the left-hand side of this slide shows the sections of the novel carbon data calculation form developed as part of this research project and their alignment with the PAS 2080 RSSB Rail Carbon tool template, which was created by Network Rail for alignment to PAS 2080. This is on the right-hand side. And this is to align the carbon emissions from the case studies with the relevant PAS 2080 life cycle stages as indicated a couple of slides ago, the A, B, C, and D stages. This research is firstly looking at business as usual. Let me just clarify here what business as usual is for the research. At the beginning of this project, back in February 2021, the current status of the Rail Safety Standards Board Rail Carbon Tool footprints were that the majority were cradle to gate that could be that were accessible to me. So that meant they included for A1, A2, and A3, which is the 3 squares highlighted on the top line there. The proposed business as usual scenario for the carbon footprints constructed as part of this research is that they be cradle to end of construction rather than the previous cradle to gate. So that means that they encompass life cycle stages A1 through to A5. Selected footprints are being expanded to cradle to grave, which is A1 to C4, the second line up from the bottom, and then a comprehensive scenario of cradle to cradle, which goes from the A0 through to the D stages beyond the life cycle. Selected footprints are being expanded into these different scenarios are the renewal footprints, because a variety of footprints were constructed based on maintenance, refurbishment, and renewal. Maintenance and refurbishment footprints, though, are themselves the B stages of larger infrastructure projects. So they are not suitable to be expanded into this whole life cycle themselves, whereas the renewals are akin to a new build. So they are therefore suitable to be expanded in these 2 ways the cradle to grave and the cradle to cradle. So at present, all 50 have a business as usual footprint, A1 to A5, cradle to end of construction, with the 5 renewals having been expanded to A1 through to C4, and the comprehensive scenario scheduled to be completed early next year, as the focus for the majority of this year has been on emissions reduction. So the business as usual scenarios have been taken and emissions reduction factors applied. However, that's outside the scope of today's talk, but it's so you're aware that that is going to take place. Moving on to a little bit more detail about the case studies and the method. The case studies are on railway infrastructure earthworks. They cover embankments, soil and rock cuttings, and they cover 3 different temporal interventions for each of those earthworks. Several examples are available for each. Maintenance with a 2-year lifespan, refurbishment with a 20-year lifespan, and renewal with a 120-year lifespan. The data for the case studies are based on case studies of around 1 chain length, or around 100 linear meters. For all case studies, the data was collected ex post works on the carbon data calculation form and transformed in Excel to the relevant units, and then input into the RSSB Rail Carbon tool using the Network Rail PAS 2080 aligned template to produce each footprint. Now this slide presents the novel carbon calculation data form. Several revisions went into this, which was improved and altered to reach this final version. An electronic copy was trialled using forms with the view to people being able to fill that out on their iPads on site, etc. However, that didn't prove popular as none were returned to me in that format. So we stuck with the version in Word that could be easily filled in and then emailed, PDF'd and emailed back to me. The main section of the form, as you can see, are details of the works, top left-hand side there, the type, whether it's embankment, rock cutting or soil cutting. We put an other in there for other projects that came through, level and lifetime, the size of the works in chains, so that this is needed later on for the functional unit, which I'll describe shortly. Number of shifts and hours on shift. This is quite a vital piece of information, as the transport of staff to site, for example, will need multiplying by the number of shifts that those staff members attended site for. There's room on the form for a brief description of the works and a photograph. Materials required for works is the final section on the first page, which is a description of the materials and a supplier's part number or specification sheet, quantity in kilograms or number, method of transport, and distance to site. This is required as the transport of materials falls in the A4 section of PAS 2080. Plant and machinery is at the top of the second page, and again, the description and the quantity of the plant, along with method of transport and distances required, is especially with heavy machinery, the ton kilometre emission factor can be quite high depending on what machinery is being transported. An engine type and hours running is also needed, as this would fall into the A5 section of PAS 2080 and the emissions factors associated with running fossil fuel plant and machinery on site. Transport of staff to site is in the middle here, so number of people and the method of transport, and a round trip distance to site here in kilometres to work out those transport emissions again for A4 staff transport. And finally, waste removal. Again, method of transport and distance, along with the final destination, so we know what's happening with any waste that's being removed. Is it going to landfill? Is it going to recycling? Here is a completed form, for example, of a rock cutting. The description of the works was a devegetation to enable inspection. It was 1 shift and 5 chains, which is around 100 kilometers. 100 meters. No materials were required for these works. There was 1 piece of plant, which was a 13-ton excavator, diesel running for 6 hours. Here's the details of the number of people on site and the method of transport and the round trip distances, and there was no waste removal here. In the next few slides, I'll talk you through the production of the carbon footprint using the RSSB Rail Carbon tool and the template. When you open up the template and put it into your folder, it is pre-populated with all the A through to D stages. So then inside each of those, you can be putting your materials, your equipment, your transport, and the requisite emission factors. As you can see here, I've exploded the A1 to A3 before use stage. There are no materials in this rock cutting. However, some proportional embodied carbon needs to be put in here for the construction plant and equipment manufacture. For the case studies, all of the embodied carbon was calculated using Keller Foundation's methodology, which is based on EFFC carbone. And this is a methodology where you apportion time based on the time the plant is on the site, the lifetime of the plant, and the number of days it is usually in operation per year. You get a weighting factor from that, and then you multiply that by the emissions factor for different categories of machinery to arrive at some embodied carbon, which is the carbon for the A1 to A3 of the machinery. This is an expansion showing the transport carbon. As you can see, it's 0 here for products and materials, but we've got some carbon in here for the transport of that 13-ton excavator, which travelled by HGV, the 90 kilometres site, as we saw on the previous page. So that those details go in here, and then we will arrive at the amount of carbon that produces. And then for the worker travel, we've put in a Ford Transit type van running on fossil fuel. As all members of staff travelled in the same vehicle, we can just add up all the mileages and put it in as one item here. If you had different vehicle types, you'd have to put in individual lines for each one with their subsequent mileages. So in this expansion, I'm showing you the construction stage, the site activities. Here's where the excavator sits. And here is where you'll put the within this, you'll put the running hours, and you'll select the correct engine type based on horsepower or kilowatt hours, which you can find either from the specification sheet for that particular piece of machinery, or if one was not available to me, I'd use a generic specification from somebody such as JCB for a similar size item of plant or machinery. This is just a quick to show you what the tool outputs. It's a CSV download that you can pop into Excel or any other spreadsheeting tool. And this lists down all the items that we saw on the screen there in all the different A categories. And it also gives you the library name that was selected, the source, which is quite important information, so you know what carbon database was used for this. Here, these factors come from DEFRA. You could also get factors from the Bath Ice database. Which regions they're suitable for, or they've been calculated for, and finally the carbon factor value that was used in these calculations. So all that detail is available to you. You can also download a PDF report, and in this reporting tool you can also create graphs, so you can do comparisons, for example, using one size excavator and another size excavator. You could compare the A5 carbon there, or if you were using materials, you could compare one type of cement with another type of cement and see what how these affect your overall carbon factors. Moving on to the results slide now. This slide is a graph of this rock cutting, detailing the carbon emissions split by life cycle, A1 to A3, A4 and A5. This clearly illustrates the carbon hotspot for this case study resides in the A4 life cycle here, with over 400 kilograms of carbon equivalent. The BAU for the A5 is sitting at just under 250, as you can see. So that would be your secondary concern, would be that life cycle stage. Now this pie chart is the same information, just to show you the percentage here, because it's quite clear here. You can see easily it's 2/3 of the carbon is in that transport carbon, and 1/3 is residing in the construction activities. So you can see that the biggest impact to reduce carbon in a rock cutting undertaking this type of intervention of a rock cutting maintenance would be to take action in the transport carbon, which is the transporting of the staff to work on the site and the transport of the plant and machinery. Now, this rock cutting had a raw total carbon emission for this business as usual scenario of 682 kilograms of carbon dioxide equivalent. If you have a look in the Network Rail Cost and Volumes Handbook, they've got around 1,608 rock cutting maintenance volumes. So if we multiply that, we get a figure greater than 1 million kilograms of carbon dioxide equivalent, or 1,000 tons. So as you can see, extrapolating these up, from these very small case studies, these figures are not inconsequential. I did mention briefly earlier the functional unit. The functional unit for this rock cutting is 341 kilograms. This is taken from the raw figure divided by the number of volumes, which is 1 in this instance, and then divided by the number of years of the temporal lifespan, which is 2 for a maintenance. So we simply half that. Some of the other case studies in the suite of 50 have, for example, 6 or 4 volumes. So you'd be dividing your raw number by 6 or 4, for example, and then dividing it by 20 if it was a refurbishment and 120 if it was a renewal, so that we get this functional unit to allow comparison between different size interventions and different temporal lifespans. Now, moving on to some discussion points. So the purpose of the research is to find decarbonisation efforts to aid Network Rail in reaching net zero. The balance here on the right-hand side succinctly illustrates the lowering of the embodied carbon in the construction, the materials, and the transport, and then the offsetting of any residual once that step has been undertaken by a sequestration, for example, which would be tree planting, for example, enhanced weathering, which could be rocks that could be spread, for example, on car parks is one of the examples I have read about in the literature, and other methods of carbon offsetting to get that residual down to zero so that we can reach net zero by 2050. Once the footprints are analysed, the hotspots can be found, and they have been found, and targeted decarbonisations in the hotspots can begin, which, as I mentioned earlier, is the next stage of the research which I'm currently involved in. So, in conclusion, there are a variety of solutions available, and production of footprints split by life cycle stage will aid in choosing these solutions. Some example of current solutions, those for the near future, and longer term solutions are given in this slide. So, as of today, we could be choosing the lowest embodied carbon materials for your cements, for your steels, for any other geotextiles. We can be choosing those. We can be switching to EVs for our vehicle movements. These case studies are obviously looking at subcontractors and their mileages. Network Rail itself has got its own targets to switch its own fleet of vehicles, which would fall under its own scope 1 and 2, as opposed to scope 3, which is the value chain, by 2027. But the target I mentioned earlier of Network Rail getting 75% of their value chain to sign up to their own SBTs, which would involve them thinking about how they're going to reduce their carbon, will hopefully mean a push on contractors to move to electric vehicles, etc., and lower embodied carbon to bring down their footprint, which in turn will bring down Network Rail's footprint. In the near future, greener construction machinery, whether that be electric or biodiesel, and electric and battery powered hand tools on site, all again to reduce the carbon. Biodiesels being something that I'm looking at in quite a lot of depth due to the ease of changing heavy machinery over to these, because obviously there's the embodied carbon in the machinery. We don't want to just be scrapping new machinery that's fossil fuel powered for electric or hydrogen even. We want to try and not waste that carbon that's already been locked into that machinery. I haven't put hydrogen up here purely because hydrogen, although zero carbon at point of use, there is carbon associated with hydrogen depending on which pathway you take for it, there being blue, green, grey hydrogen. So a bit more thought into which hydrogens could be used and whether they would be used to power machinery or to power battery banks, as is done with HS2, to then power machinery on site. Moving on to the longer term, offsetting, such as planting trees and enhanced weathering of rocks, are just two of the options I'm exploring. And these are more from the academic literature, but also from the GGRD projects, which are the greenhouse gas reduction demonstrator projects. They've been taking place for about the last 2.5 years. They started shortly after I began my research project, and they're looking at biomass and biochar. They're looking at sequestration. They're looking at peat bogs. They're looking at enhanced weathering. So they're looking at scaling up activities that are in the literature and are not in full scale production at the moment. So it's about taking things from the literature and novel methods and how we could use them long term and what the real benefits are to using those. So that's something that I'll be looking at the beginning part of next year as I summarize the sequestration and the offsetting that is required to net zero the residual carbon from the emissions reduction. Let me just come on to one of my last slides. So in summary, this presentation is focused on a data collection method using a novel carbon data collection form to ensure consistency in data collection and allowing for production of PAS 2080 aligned footprints. Other considerations for further exploration include movement away from linear to whole life cycle. So instead of take, make, waste, we want to take, make, and instead of waste, we want to be feeding things back into the supply chain. This is discussed further in my paper, Carbon Footprinting of Railway Embankments and Cuttings, a Circular Framework. But also, Network Rail has a case study of Acton Underdive, which I alluded to earlier, I believe, where they reused the soil from a project in the local vicinity for landscaping. So no soil went to landfill, which is a great win and a great example of the circular economy. Standardization of footprinting across the industry via use of this data collection method will also be discussed further in the upcoming paper, which this presentation has been about. And just the last few slides, I've put some resources there for the Rail Carbon Tool link, which is free to use for anyone in the rail industry in Great Britain. This is just one of the front end pages where you can see there's a lot of information about the tool, the guide for network rail infrastructure, the introductory guide, various user guides and how-to guides. There is also training available for a course that you can go on, which I'd highly recommend if you're going to be doing lots of carbon footprinting for your company or for academia. And this is just what the front end of the tool looks like. So you can see when you go in there, there are various places for carbon factors, your sandbox for your own projects that are shared with others. There's limited visibility of other people's projects in the tool because it depends whether people are sharing them, although there is a new carbon note that's come out from Network Rail about which projects they want to see being footprinted and how they want them saved so that people can view them. And finally, that's a list of papers that I have currently in publication. And there you go. Any questions? I'll just stop sharing there.
Okay, thank you very much for your presentation, Tracey. So I invite everybody to write your questions into the chat box. I'll just take a few minutes out of this question and answer session to remind you the next Lunch and Learn event. We which will be on the 21st of November. And the subject is the TFL Emergency Response Unit. So this presentation, I remind you, 21st of November, is about the organization, the scope, the equipment, and the capability of the TFL Emergency Response Unit. And the presentation is also outlining the part that the Emergency Response Unit has played in some notable incidents. I kindly ask Jack Scott to switch off his camera, if possible. Okay, so let's start with the questions. Dave is asking to have Tracey, your email address, but at the end of this presentation, the end of this event, we will write her email address in the chat, of course. Sankardev is asking how were emission factors calculated in development of the RSSB tool?
Right then, thank you very much for that question. In the RSSB tool, there are the Bath ICE database, which is from the University of Bath. That was developed back in, I believe it's 2009 or 2011. I'll have to look up the exact date for you because there's different versions of the Bath ICE database, but that is one of the UK databases. And also there are DEFRA figures in there from the various government factors, such as they publish annually GHG conversion factors. So if you actually look at the 2000, in my research, I've looked heavily at 2018 at the beginning and more recently at the 2023 factors, and you can see that emission factors are coming down, mainly as all other parts of the UK decarbonise. It's bringing all the emission factors down in manufacturing from electricity, for example. New factors are currently being developed. The BECD, which is the Built Environment Carbon Database, was released early last month, and they have asset level and product level. I believe the product level, last time I checked a few days ago, wasn't online. There's been a technical problem there, but that database will feed into a new Bath ICE database. And I know the RSSB tool does update, but you have to check when you're putting in your factors which version of Bath ICE you're putting in. There is a choice, for example, version 1, 1.6a, version 2, and the latest. And as I say, a new version is due to come soon. I'm just reading ahead on the next question. I'm trying to find the answer.
Okay, thank you very much. The next question is by Matthew. Matthew is asking if you can give a brief explanation on the differences between blue, green, grey hydrogen.
Okay, I've just looked up that answer whilst I was waiting there. Right, grey hydrogen is they're all via different pathways. The pathway for grey hydrogen is methane reforming without carbon capture, use or storage. So CO2 is emitted into the atmosphere. Blue hydrogen is methane reforming with carbon capture, use and storage. So between 95 to 97% of the carbon dioxide is stored or reused. Green hydrogen is electrolysis using renewable electricity and no CO2 is emitted. And then I've just got a hydrogen type of hydrogen, which is biomass gasification with CCUS, and that will deliver negative emissions. So, and those explanations are taken from UK National Grid 2020.
Okay, the next question is by Samuel, and Samuel is raising a question about large-scale projects, such as capital delivery projects. Did you draw any conclusions on the level of effort required to account the vast activities and the actualization of where carbon hotspots sit?
This is for large projects.
Yes, very large projects.
No, my focus was on these small micro case studies. I've got a suite of 50 very small interventions, because large interventions such as HS2 and such as huge line improvements have a lot of focus and attention. And in the literature, you'll find reams of data about large infrastructure projects. So the focus on this research was on smaller projects, with the view to the multiplication of these by the amount of these works that are going on across the whole of Network Rail each year. They're sort of a forgotten part of the carbon, because each one individually is very small. But as I showed you in the slide, when we multiply these up by the number of interventions that occur every year or in every control period, as Network Rail works in its 5-yearly control periods, they're not in inconsequential amounts. Does that answer your question? I hope that does.
Okay, thank you. Purnell is asking, so maybe I kindly ask Purnell to switch on his microphone, because I think that the question is quite tricky. So maybe if you ask it directly. Okay, Samuel, can you ask the question directly?
For Purnell's?
Thank you.
Yeah, well, I think he's just making more of a statement of the carbon capture tool looks good in the form that Tracey presented. Just a general comment, and we could probably work a bit better towards all doing this and all kind of working towards a circular economy. I don't think there's a question, just more of a statement from Purnell.
I can pop the link to the Acton Underdive case study. It's sort of a flyer that Network Rail have put together about the reuse of the soil, because I think that's a particularly good example of reuse, because they thought not just about reusing the material, but about using it in the locality. Because as I found in my studies, the transport distances of some materials and plant are quite large, considering how big the UK is, and use of materials and plant locally could help to reduce the carbon footprints further.
Okay, then we have a question by Dave. Dave is asking, how does enhanced weathering offset?
Okay, enhanced weathering. What it is as the rocks are exposed to the weather, as the name suggests, they weather, and they actually absorb carbon from the atmosphere. So they actually gain a bit in weight as they gain carbon dioxide. It's a very long process, though. It is something that's being trialled in other countries on a small scale. I'll have to dig out some literature I've got on this, but I believe they've done sort of ideas where to put these rocks, and they're a special type of rock that absorb carbon along sort of maybe track side, not in the back, not in the area and the zone where the rails are, but potentially access footpaths or car parks, just to increase carbon sequestration. There is more about these if you go to the GGRD website. I'll have to find that link as well and pop that over to the WPI, and then you can have a look there at all these are the greenhouse gas demonstrator projects, removals demonstrator projects, GGRD. And they are doing a lot of work into real life applications of enhanced weathering, biochar sequestration, and the like. So I think there's 5 different demonstrator projects, and they're all looking at these specific aspects of sequestration and greenhouse gas removal.
And how long is this process? This is my personal question, if you can answer.
It can take several years. It's a very slow process. Okay. It's not a magic bullet process. It's just, if it was done at scale, there've been some large scale studies on sort of farmland where it's putting in as an additive to help with the nutrients in the soil, but it also they found that it has this added benefit of sequestering carbon, but it's very small amounts. I'd have to look up exact percentages though.
Okay. Thank you very much. The next question is again by Sankar Dev. Can you please explain how does carbon offsetting reduce GHG? There are several questions by Sankar Dev. What if developing countries offset? Who benefits from that? Is time to be fruition considered into the offsetting benefits of for entire planet? So if you can make
okay, well, I'm not looking at the entire planet. I'm looking at my particular case studies, and one of the things with the offsetting is there is a WCC carbon tool where a biodiversity tool where you can put in examples of different tree species, and it will give you an estimate of how much carbon they will offset in certain time periods. So after a year, after 2 years, 3, 5, 10, you can use it like that. And what I'm doing is with each case study, I'm applying the emissions reductions hierarchy, which is the paper that's in production at the moment for next year. And that will be a hierarchy of which reductions for which type of interventions and which order they need to be done in. For example, the rock cutting example we showed had a lot of carbon in the transport stages. So it would make sense for that type of intervention to have for example, electric vehicles and use of biodiesel higher up in the hierarchy than other interventions. So once that intervention has been applied to reduce the carbon, you're left with what's called the residual carbon. So you've reduced everything you possibly can. That's what's left. That is the amount that will be offset by a number of trees planted. But it would just be, I would just be looking at the number of trees to be planted for that residual for that one project. Once you start looking, if you looked at the original carbon, there wouldn't be enough land in the UK to plant trees to offset that. You've got to reduce before you offset. And so look, what if developing countries offset? Who benefits? Well, offsetting benefits everybody as a whole because you're offsetting it. There's only one planet. All the carbon, we're all exposed to the same carbon, although obviously some developing countries feel it that the climate change, the results of climate change more than the developed countries, but that's more of a global, where you're positioned in the globe as opposed to who's offsetting and who's not. There are a lot of projects out there about desertification, about bringing regreening places in Africa, etc., and in China, but the benefits of offsetting is obviously at a global scale, but obviously the other way of looking at the benefit is an accounting method. This is an accounting exercise. So the carbon offsetting would be, we reduce and this is how much carbon's left, so we therefore need to plant this much trees to be able to say that is net zero.
Yes, so the benefit is for the whole planet.
Yes.
So there's a question by Mokram, and this question about carbon capture and storage. You didn't talk about that, but if you know something, if you can apply to this question.
I'm not an expert on carbon capture and storage. I'm aware there's many different types. How safe? That's really outside of my sphere. I would direct you to the literature for that one. There are the CCC has various documents, and if you do a simple maybe a Google Scholar search for carbon capture and storage, you'll find that. But basically, economically and environmentally viable, it depends on where you're trying to capture it, because there's different kinds of carbon capture. There's people who are trying to capture it out of the air. When it's a few hundred parts per million, that's obviously very difficult and obviously not the best way to do it. Other ways that this is being used is mainly from what I've read in industry, for example, at cement plants and steel plants, which are heavy carbon emitters, is locking up the carbon from their exhaust pipes. They basically have apparatus that is inserted in there, and then it will absorb in whatever method they've chosen to use. So I would say, as a general indication, carbon capture and storage with these units that are just placed out in the air is not particularly economically viable or environmentally friendly, because there will be carbon expended in building these mechanical units when we've got trees that do this perfectly well. However, it depends on what we need to do. We may need to deploy all actions to get the carbon levels down. It depends on how on whether we're meeting our targets. So it's, on the one hand, it could be said to not be environmentally and economically viable, but it depends whether we're looking at a very small scale or at a global scale. At a global scale, it is sort of known that we will need to have a multifaceted approach. So there may be a place there for carbon capture and storage units, carbon capture and storage at the place of emission, plus sequestration, enhanced weathering. There's a whole plethora of carbon capture techniques out there, but where they need to go and how many of them need to be put in different places is a question outside of my expertise. But there are there is a lot of literature out there explaining all of this.
Okay, so maybe it is not economically viable to date, but in the next future.
It may be in the future, yeah.
Yes. So a very interesting question by Simon. This is a financial question. Is there a direct comparison with CO2 cost and financial cost across the model projects in your research? So the question, if I understand it correctly, is about how much would be the project cost raising in consequence of this additional interest and attention that should be paid.
Okay, that section of the thesis is not yet complete. Once the emissions reductions are complete, I will be doing a cost of carbon, because I do have the costs for each individual project. So I have those costs from Network Rail, and what I'll be doing is, obviously I can put a cost, a carbon cost per £1,000 spend is one of the metrics I will be looking at, but that exercise is not yet complete. It's been undertaken for the business as usual, but obviously it needs the comparator of the emissions reduction scenario to see what the difference will be in implementing these actions.
Okay. Hannah is asking if you have carried out any exercise incorporating biodiversity.
Okay. I've not done a biodiversity exercise per se. When the sequestration is investigated early next year, I'll be looking at the number of trees and looking at those as an area of the site, because Network Rail itself has got biodiversity targets that it needs to meet, as in no net biodiversity loss by a specified date, and then there is actual a requirement to have biodiversity gain at a later date.
Okay, another question by Charles. Hi, Charles. He's asking something about electric vehicles. So he's saying that maybe the power generated from electric vehicles would hopefully not impact productivity as compared to that of diesel vehicles. And so he is asking whether there is any publication that explains the thoughts going into this process, such as trials, experiments. If you have any experience on this.
There are several papers about NRMMs, non-road mobile machinery, and the emissions. A lot of the focus on the heavy plant and machinery is on pollutant emissions and particles in the air, as opposed to carbon dioxide. But there are papers out there. I'll have to make a note of that and pop some and pass over some details to the PWI of some papers I've come across on that. But there is some publication on that available.
Someone is asking whether there is any research looking at the practicalities of enforcing this type of carbon review by project team supply chain.
Well, at the moment there is practicalities. There is a size of project that has to be carbon footprinted. It's in the carbon note that's been sent from Network Rail. I can also pop that. I can also pass that over to the. But there is a it was released. It's on the Safety Central site. There is a carbon note, and it's about using the tool and what size project and what levels and scopes need to be included in the footprint of those carbon footprints.
Okay, someone is suggesting that the ENV 015 is the dedicated standard about this subject. Then Martin, is the carbon emitted due to closure of railway included, i.e. greater use of road vehicles to replace trains?
No, I've not done any modal shift in these calculations, but a lot of these works are very short works. They're sort of a 4-hour shift devegetation of the line side. So I wouldn't like to say whether they would have closed the track for that works or whether they would have done it during a down period.
Okay, so the very last question. Do you consider the life cycle of the planted trees themselves? Presumably they will need to be harvested in 20 or 30 years, and much of the tree mass ends up in temporary products such as construction chipboard or toilet roll. The carbon in these products then returns into the atmosphere when they are landfilled or incinerated. So this is a comment. If you can say something about that.
Yes, I do consider that, because when calculating the number of trees that would be needed to offset it and the life of those trees, that would then need to be maintained in perpetuity. So if it took 10 trees to offset a particular project, you'd have to maintain those 10 trees in perpetuity. So you'd have to look at the carbon, obviously, in masses over time in a rough sort of curve. So you'd have to look at when you'd need to plant the next set of trees to replace those trees at their end of life, or indeed when they're harvested. So yes, you would have to look at that, because you would have cycles of growth, and then obviously when they're chopped down, you go back down to zero, and then you'd have to grow again. So you'd have to very carefully plan your sort of tree planting regime.
Okay, thank you very much indeed, Tracey. This was an excellent presentation, and thank you for the experience you have brought to this event. And thanks everybody for attending this event. And I remind you again that the next event is on the 21st of November.